Thank you, Elena, for introduction. I'll have the pleasure to chair the session and to start my talk. As always, mornings are very busy, right? So, yes, but I have to find my presentation. Yeah, okay. First of all, I would like to welcome you all and to express my gratitude to our sponsors. I want to announce that we have a message from the Minister of Economy, Trade and Industry of Japan, Mr. Seko Hiroshige. We have been, Aquaphotomics as a discipline and is opening, obviously, a future that we all are aware, but needs a deep ground. And this conference is all about this. There's so many things in our life that have not been explained. And today my lecture is why Aquaphotomics. If there is still a question why, I just want to answer it if I can. With the workshop yesterday, I was so pleased and happy, and I can't explain the level of the data analysis that we have at the moment is very high, and it's going to be even higher, I know. So we know we need new methods for data analysis that will help dig down and understand more and more the spectra. So, and I really appreciate the presentations of all members, especially our friends Zoltan and Bernhard, that they have developed the software devoted to Aquaphotomics, and I'm sure they will develop it further. I'm sure they learned a lot yesterday as well, and we all have a very good community, and this is what we are starting to do, is to develop this community and assure that we have the tools and develop the tools. Okay, so I will have few slides. We have new people coming this morning, and just a kind of introduction to Aquaphotomics. When we say Aquaphotomics, I think everybody at the moment, I myself have expanded. I expanded this definition with the years, and now Aquaphotomics is a water mirror, so we know that. But it's a collective mirror, and this is when I realized it. It was very, very a special moment, because it is a mirror not only of it is not only molecular mirror. It water as because of having hydrogen bonding, and always when I say hydrogen bonding, I stop for a while. At the moment, with the knowledge that we have now, we use the word hydrogen bonding. So we don't know what exactly is there. But to understand each other, now we use this term, and we are going to use it until we know what's happening. But we will start using our vocabulary. So we start to develop our vocabulary, which means we'll use water matrix coordinates, the bands that water absorb energy from the electromagnetic spectrum that we know. So these will be our letters. And the specific patterns that water has will tell us the functionality of this water. It is a holistic marker. Okay, aqua, photo, Omics stays for water and light interaction, and all about. Omics is, it's a very heavy responsibility on the shoulders. So we have to know all about the interaction between water and light. And this is a fascinating area, and this is really a fascinating journey, which all of us have opened, and we have to give it to the younger generation for the future, because understanding water is really a privilege, but the privilege always goes with duty. So it's heavy. So, and one thing that we have to realize always, is that light is not the tool to dig out information for the water, but the light is simultaneously a perturbation. So it is quantum mechanics stuff, it's quantum field theory, but we have to be aware of this. It is simple. We're measuring, we influence the water. Now, X-ray people, and they know it because they cannot use the sample after they measure it. But near-infrared people do not realize it. People that use near-infrared lights do not realize it very much. But it will come that near-infrared light, as a half of the spectrum of the sunlight, might be very, very important for our bodies and for our life. And having this light shining on the water might have a very important function in our lives. So this is realizing that light is not only a tool to analyze water, but it is a source of energy and a source of perturbation that changes the water in a way to scan the rest of the media, everything else but water. Because when you shine light on the system, water absorbs light, and by absorbing light, it changes the conformation, it changes the structure. So, why change the structure? Because of the energy coming in, and because of the molecules inside, and because of not only molecules, but because of the external energy fields as well. So, traditionally, spectroscopists like to have spectrophotometers, and the criteria for a good spectrophotometer is to repeat the same spectra 1,000,000 times. If the spectra every time is different, the instrument is not good. Well, this is not anymore so with the water. So we know that the spectrum of the water next time will be different. Okay? So, now why I have this slide? Just to remind you that we have sound also as a source of energy, and sound goes always with infrared light, and infrared light has overtones. So, and I'm noticing this because this is a source of information, and we had Rasmus yesterday asking questions and mentioning octaves. So octaves and overtones is the same thing. And we might be able to find, we are working on that, to realize that actually light and sound at a certain point are doing the same thing. They are perturbations to the water. They change the water, and they might be, at a certain point, be our feedback to influence the water. Remember, genomics arrived 20 years ago, even more. Then we had genome, and we started this genomic engineering that now is called bioengineering. So it puzzled me for a long time why genomic engineering should be bio. Bio is much, much, much wider. Now I can see that if we know water better, if we know which are the sources to influence and restructure the water, we can do also, maybe one time water engineering, but water engineering won't be dams, etc. It's a bio-water engineering, maybe. I don't know. This is just very, very far in the future. And this is something that I will tell you how I imagine this. the science at the moment is reductionist science. So we go very deep in a very narrow areas. And we have conferences on vitamin B, single molecule, and prion protein like this, millions. Now, but people don't talk between themselves. And we have metabolomics that is going to try to find a connection to analyze all the molecules. But the problem is that it is destructive. And we're going to have a wonderful talk from Dr. Ikehata about the connection between omics and aquaphotomics. So I imagine all these omics disciplines as a vertical sciences, parallel, and aquaphotomics as a horizontal, a holistic. So we have the knowledge about water will give us the connection between all these other molecules and energies that are influencing the system. By being able to influence the water, we might be able to restructure the system, which means to obtain a new function. But how can we change the water? We can change the water by adding certain molecules, and all the knowledge that we have now with all these omics theories are preparing for this. They are preparing the knowledge for this. So we'll know which molecule changes water in which way, so we will know which molecule we need as a feedback to the system to restore the stability or functionality. Of course, we have to know that water itself is an incredible regulator. It's a self-regulator. It self-regulates itself, which is amazing. So I hope one day we'll understand this. Well, at the moment we have these big instruments, lab bench, top instruments that can provide spectrum with very small steps. And why? I want a small step and more information about the water spectrum, because more information, more knowledge. Then we have these portable devices that Japan and other countries are also speeding up the development of these small instruments that we can. All we need is just to have, like in the mouse case here, this is a fiber optic, and this is the fiber optic that gives the light and that transfers the light after that is coming through the brain or through the gut. So this is an experiment with prion disease for diagnosis of prion disease, very successful for 2 consecutive years. Repeated at the same bands, highly related to oxidative stress. And this is another newly developed sensor with all these are in the silicon, all these bands are in the silicon region, which is very inexpensive, and it can go very small. And this is again the spectrum of the water that, well, as a joke, so we wake up and go to bed with the spectrum, okay? So this is the near-infrared region. And I had a question yesterday, a very good question. Why near-infrared? What is better from other areas? It is in the middle as absorbance, so it allows the light does not get wholly absorbed. We give information from the light that has not been absorbed, so we could curve the spectrum of the system and use the spectrum as a holistic biomarker. Now, it is a busy slide, but my point is that when I saw the spectrum, I was amazed by the fact that water absorbs everywhere, through all the electromagnetic spectrum, and it is the only unique material that does this. What does it mean? That water has inside probably all possible materials, so elements. But this is very interesting that water is present at various scales from nano to macro. I think water itself, water conformations are from nano to micro. And also, water has fractality. and water can explain phenomena from micro to macro scale. So this is something that desires more attention and more work, I think. Now, how the water spectrum looks like. This is the water spectrum, because from now on I will talk about, thank you, the first overtone of the water. As you can see, it's a flat, it's a wide band. So usually people say, what can you see? No, we cannot see anything by our naked eyes. So that's why we need data analysis. And that's why we devoted a whole workshop on data analysis. When we analyze this data, look what we can see. Underneath this first overtone, we have so many different water bands. And this is with two-dimensional correlation spectroscopy analysis. We can, as yesterday you saw, we could see specific bands for specific solutes and specific molecules and fields influencing the water. So if we diagonal cut is like this, and if you start remembering, maybe you need this, so we all need. The first overtone starts from 1300 here to 1600. But these are the water bands. These are the bands that we see when we take consecutive spectra of the water. And these are so-called water matrix coordinates that are the specific water bands that are coming out when we analyze every sample. Now, this is the second and third overtone from 600 to 850 nanometers. People usually say this is visible light, yes, up to 680. But then but visible light also has the fourth and fifth overtone of the water. So all these wiggles are specific information for the water. And this is very interesting. Look, if we take spectra we have a water in the cuvette, in the instrument, and we start taking spectra over the time, and you could see these time features. These are changes over the time. These are fluctuations of the water that we can observe non-destructively, non-invasively. So if we can read these fluctuations, if we can understand that, we have a band. You see, at this particular band, we don't have these big changes with the water spectrum. But at the rest of the bands, we see fluctuations. So different band means different structure, means different dynamic of that structure in the water that we can observe non-destructively over the time. Why I am saying that we are working with four-dimensional system. We can observe these three-dimensional changes in the time, over the time. So what do we need to do? We need the perturbations always in order to activate the water. It could be temperature, it could be analytes, other analytes, could be humidity. We acquire spectral data, and why infrared? Why Aquaphotomics was born by working with infrared? Because we could do this monitoring, biomonitoring. We could see these influences of the water in the spectrum. And then we need this. We need data analysis in order to catch the water matrix coordinates and to make the aquagram. This is the aquagram in the first overtone. I think from yesterday you started remembering these 12 bands for now. But a different system have a bit shifts, and every system has its aquaphotom, the water matrix coordinates plus the specific spectral pattern regarding each perturbation. Now, so water molecular system has many conformations, and each of these conformations has been assigned. I don't think each of those conformations have been. We still have probably things that we don't know. But this one example is like we have different number of water molecules with hydroxylated cluster. So people use the word cluster. I'm not sure that we're right. Why? Because all these conformations are connected between themselves. They influence each other. So cluster is something that is isolated. They are not isolated, but they are like in yesterday, so in the society you have different conformation of people, we connected between us, and we simultaneously play different roles. But now, in nowadays, we have softwares based on studies in infrared spectroscopy that can give you the exact frequency, the absorbance frequency of certain conformation of water molecules, certain structures. So we could just go to the software and see the main absorbance bands in the infrared range and calculate the overtone in infrared. This is what we did for already since 2005, 13 years. So, and these bands we have calculated and found them experimentally. So in different experiments we found 12 bands. In every wheat or blood or milk from healthy cow, from sick cow, we have different combination of these bands in the spectral pattern. These are the bands. We don't show here intensity, which is very important when we talk about spectral pattern, but we show which bands are activated. And this is a assigned band, this is coordinate 1 and 2, and every coordinate has a meaning. Now we lined up this with the sources of assignment. And this is also, these are the wavelengths in the short second and third overtone also assigned. It's very difficult to assign second and third overtone, but still we have to do it because it gives us connection between first and second and third overtone. Okay, Aquaphotomics, so it's the entire complements of water metric coordinates and spectral pattern. This is the aquagram, so I'll speed up. Now, I will show you a few systems. Today I want to, we have Livio Giuliani arrived this morning, and I think I'm going to make a present for him now. So Dusan wrote a paper, and he discovered the specific dehydration band when he had different salts in water. These are the raw data. This is the raw spectra. You see at different salts with different, and we have the different specific bands for each of the salts, but this is the dehydration and hydration band. So this is how we know. We perturb with a certain element, and then we see how water reacts, and then we identify, because salts do not have absorbance in infrared range. So it is not, this band is related only to water. This is the first overtone of the water. Now I'll show you aquagrams from milky water, tap water, water with 0.2% salt and acidic and alkaline water. Here. So if we have, just to realize that aquagram is very important when you calculate that, it is normalizing also. It depends on the group of the samples inside. But still, when we have milky tap water, all of the waters, this is how they look like. So you realize that different parts of the first overtone are related differently to these analytes. Now, and these are many experiments that we get absolute repeatability. Now, we take away milky, we stay with tap water, which is in the center, and then we see the rest of the waters, how they behave, absolutely the same. With how we read this, for example, you have the salt with high solvation, increasing the solvation capability of the water, and increasing the, this is protein hydration, this is tetramer, this is pentamer. So, in the water. So we know every single wavelength, what does it mean, what kind of structure, and we know, this is very important by the way, these are the trapped water molecules that we have with the salt only, not with the rest. Now when we take away tap water as well, so we stay only with this, and we see why we need the salt in this life. Okay? But we don't need only, we need this, and this is the dimer. In the next lecture, Craig will talk about dimer, and I'm really looking forward, because dimer seems to be very, very important. And Yelena also, I think she's going. Now, if you have DNA in circular DNA, double-stranded circle and single-stranded, so we'll see the differences between the two. So these are different DNAs in the water. Oh, sorry. Oh. Well, I hear I had identification, but the point is, remember, this is how DNA is shaping up the water spectrum. And these are the important bands that are related. We could successfully identify circular DNA from straight. Prion protein, well, I'll go faster, but just to show you different isomers of prion protein over the time. You see absolutely different spectral pattern. And by the way, one of these is the isomer with mangan inside that makes prion protein fibrillate. This one, with mangan inside. Now, and we could identify them as different groups, with mangan, with copper, without anything. The spectra are different. So they have different, this is only the first overtone. These are the second derivatives. Yes, I agree. When we do the second derivative, we lose information, but still, we could see difference in the spectral pattern. Here are the comparison, and this is the spectral pattern that we have the Omics, have the positive or negative the band is, and this is the spectral pattern that we use to identify. Actin. We have this filamentous F-actin and globular. This is a monomer, and you see variations. This is just actin, F and G in the cuvette over the time. We monitor, and you see all the variations that we have we get with G-actin and this filamentous F-actin. They're different, and we could identify. Imagine in a sample, we have in infrared spectra and in the water first overtone, we could identify these two proteins on the top of it. We can follow the changes of their structure. Okay? They're so different. This is a classification method. We use Simca, and we see the difference between this, and we can explain the difference. Here are their specific spectral patterns. This is the assignment. These are the spectral patterns of actin G and actin F. Now, I have a few slides about our topics that we are working now on. One is bacteria. So what we found about the bacteria is that with the spectra of bacteria in water, we could identify the stage of development of bacteria. By the way, bacteria is changing the water structure. So we could say if we are in the lag phase, or in the log phase, or in the stationary. So we might be a little bit more ambitious, and we might be able to identify even this transformation in between stages, but we can see them. Now, we had slow developing bacteria and fast developing bacteria in the growth, very fast growth and slow growth bacteria. And we asked the question, by this part of their spectrum of the development, can we make a prognosis if this bacteria is fast growing bacteria or it's slow growing bacteria? This is the research of my master student Nakagawa, who is staying there and doing the registration. Amazing. So this is the specific spectral pattern for lag phase. This is the specific spectral pattern for log phase, and compared to the water inside, in the middle. What can we see? It is very interesting. In the lag phase, all the water is hydrogen bonded. Mostly hydrogen, predominantly. When you compare, when the development starts, then we have this engine. All the water with lots of hydroxylated clusters is working. This is the working water. This is the energy. Now, we found that we can identify which bacteria will grow fast. And this is very interesting. How? By, you see, this is the spectral pattern of the lag phase of fast-growing bacteria. The difference is that in the spectra, even in the spectra, this part is this part. Even this is predominantly hydrogen-bonded structures, there are structures that are preparing the development. This is very interesting, very interesting. So, and when we did the assignment, look at the assignment. Lots of protonated water clusters, and especially hydronium atom, Livio. Yeah, this is the hydronium. Livio wrote a paper in 2015, and he and his colleague, they stated, our results indicate that hydronium resonance stimulation alters the structure of water, enhancing the concentration of easy water. Easy water is water that is, this is on the surface of hydrophilic naphion, the hydrophilic part of the naphion. So we will be talking about this water. Jerry Pollock is coming in, and this is the phase of the water that he talks about, and he actually shows this easy. He calls it easy, but this is the water has been discovered by in 20th century, 1960s, as a water conformation that gives lots of energy. I mean, it's hydrogen-bonded water that isolates. Its exclusion zone means excludes everything. So it's only water. It's very pure water. There is nothing. So now we have lots of hydronium, and the hydronium band is 1438-36. If you want to remember, this is going to be very, very important. Now, this is a study that Christina Maligori, this is in a collaboration with her and her colleagues. We're going to submit the paper. She wrote the paper already, but I just allow myself to show you, this is the germination of rice, and in preservation, this is the water activity, high, middle, low, over the time. So different color means different time, but this is the hydronium structure. So this is high water activity over the time, and this water activity, this hydronium, structures the water like this. Lower activity, different structure. It's beautiful. It is beautiful. It works. Livio, it does. Yes, so we will have, and this is the last example, so keep fingers crossed, we might get this published very soon. This is a plant that survives. It's called resurrection plant. Resurrection plant is a plant that can stay 2 years as a powder without water, dry. If you add some water, it becomes green. So, and we asked the question why. So we monitored at different hours in different, this is the control, and this is the plant that survives. What you can see, different color means different water structures. These are the S0 are free water molecules. And this is with one hydrogen bond with 2 and 3 and 4. So we're talking here about the dimer, and this is the dimer, and then the main, if you could see, S0, the free water molecules, is something that the free water molecules and the hydrogen bonding, this hydrogen bonding water, is so nicely controlled. This is dehydration, and this is rehydration. When the plant dehydrates, this plant, which is very interesting, this plant, 1 hour, or 6 hours, Elena will talk details, but I think this is the 6 hours result. After 6 hours, loses all the water, keeps a little bit, keeps only the quantity of the water that this plant needs to make the regulation of its own system. We people try to keep everything, so we die. This guy tried to keep this free water, and free water is very aggressive. So, and tetramer is very important as well. So what this guy did was he lost this free water and lost at the end very much, increasing the dimer. This increase of the dimer is so important. So, and with rehydration, the dimer starts diminishing, and then we have this tetramer and hydrogen bonded water that also diminishing. Obviously, this clever plant survives because it has a system to regulate its own water structure by sugars, amino acids, etc. So, how I see the future, I'm a little bit late, but you forgive me. So what we need to do is we need new interactive instruments. Interactive means that we need an instrument that can do the perturbation at the same time. Then we need new powerful methods for data analysis. We have to develop further and further aquaphoton with the water absorbent bands over the whole electromagnetic region. Then we need a very deep, to deepen to know the meaning of perturbation and the relation between the perturbation and water structure. And then we need integration with other omics disciplines. So we have, the previous conference, we thought that we need to start establishing an International Society of Aquaphotomics. And I think we can do this at this conference. So I invite you today at the end of the sessions to talk about this and establish the first International Aquaphotomics Society. So these are the future. This is the future in general. I mean, these are all the areas that we can solve so many problems with this approach, I believe, but we need to do all this. Thank you very much for your attention. Thank you. Now, because I'm the chair, so I will get a few questions. Go ahead, Kurt. Yes. Can we have the microphone?
I got it here.
Yes, okay, thank you.
Thank you so much, Roumiana. It's another wonderful presentation. So 2 quick questions. So the effect of IR perturbation, how long it will last? I mean, the IR perturbation from the measurement itself, how long that will last?
A very good question. I talk for perturbation, measurement as a perturbation, which means that it lasts the same time as the measurement lasts. But it is something that we can, we need to experiment also to see how long it should be, because I believe that when we have different time of perturbation, of course we will have different information.
Yeah, but is that part of the protocol of Aquaphotomics?
Yes.
Okay.
Just the measurement is the answer.
I think that partially answered my second question, but I still just ask anyway. The main reason triggered me as the first question is because, let's say a random arbitrary example, you have 2 raw milk from 2 different cows.
Yes.
And I think it's only fair to assume when you measure the 2 raw milk, they had previously different baseline due to the perturbation unintentionally.
Yes.
And then how to decipher the intentional perturbation during the measurement and the previous perturbation, whatever happened at the cow.
Okay, understood. I got you. Whatever. I mean, these samples are different. So, and they have been through different circumstances. Fine. We have these samples as an object of measurement, so we measure them. We introduce the same perturbation, which gives us the right to compare them at the end. So of course they're different, but they absorb different influences differently because they are different. But we know what exactly perturbation, we can control the perturbation, we can explain it, and we can repeat it. And this is the point. So if we repeat the same perturbation, we get the similar results. So we can identify these two milk samples from different cows. Thank you. Other questions? Yes. Academic Polishev.
In your observation on the water, all this dissemination of the spectrums, ultraviolet mirror of molecular structure of the water, depend maybe, I suppose, from the salt substances in the water itself. Even pure 100% water.
Yes.
How you take into account the salt substances in our measurement of this?
Okay, so I'll take your question as a question. How can you control everything that is in water? We cannot. And we don't know what exactly is in the water. We don't know even exactly what kind of, all of the structures, as I said in the beginning. But our point is, with the perturbations that we can introduce, and we know that these perturbations, and we can control the experiment, we make certain specific structures that we know in the water active. We cannot know everything, so let's be modest and just stay with what we know, step by step, because now we know we can control and we can see these conformations. With another perturbation, we can see another conformations. That's my answer. We cannot know everything in the water. That's true. Thank you. Other questions? Yes. Yeah, you can go, yeah.
So my question is related to the different overtones of water. So you have done work in the second and third overtone regions of water. So if you want to compare the first overtone with respect to second and third, so which one is easier for aquaphotomics?
Okay, thank you. Wonderful question. First, I've been working with first overtone predominantly because it is easy for assignment. Then the bands are overlapping in the second and the third, and it is more difficult to of course, the information. On the other hand, the second and third overtone is rich of information. There's lots of information. We have also electron transition information on the top of it. But for knowledge, to build up gradually, to understand what is happening, the first overtone is better. To know, for identification, for assignment, we use the first, and then we can, the second and the third are rich in information, what it is difficult to identify, and the second and the third is very easily influenced by surrounding.
Yeah, I can also feel the same thing. Like I'm working with fruit samples, so for the non-destructive measurement, we have the 600 to 1,000 nanometer band, and we can see a lot of CH carbohydrates and water, combination. So it's pretty hard sometimes to find out water bands.
Okay. Thank you very much for the question. Why? Because I think we have to be very careful with this. In infrared literature, lots of bands have been assigned, like CH and NH and etc. But also we have to be careful and realistic. The second and third overtone is a range where the absorbance of molecules is 10,000 times or 1,000 times less than in the infrared. So when you have a fruit, when you have the water content is above 60, 70, 80, so can you see really a CH band there? And can you measure really the CH band? So it is always on the top of CH we have water. So this is something that we have. So you have to perturb the water to see if this band is perturbed perturbed by the water, and if it's really CH or it is some conformation of OH band. Okay? Okay, thank you. I think we'll stop here, and Olivio, yes. Yeah.
In your investigation, did you find more difficulty in characterizing the solvatation of cation as the solvatation of anions, or there is not a symmetry in this effort?
Thank you for the question. I will leave it for Dusan. He has a presentation, and I think he will answer the question in details. Yes, there are differences, but Dusan, are you here? Dusan, I cannot see you, but I hope you can. He has a presentation. Okay, thank you very much for your attention. So we move on. Our second, thank you.